Alright, welcome back ladies and gentlemen. I was recording that video and my phone died. Very inopportune moment. But we still have everything on the board, so we're just going to make this a two-part video and we'll work from there. Okay, so just a quick recap. We have the ball. We have 9 different cycles of position we're going through, and we're looking at the position, the velocity, and the acceleration at each of those points. Also, this is a description of simple harmonic motion, or SHM. Now, we were looking at point number 3 and how it had extended to its equilibrium position, which is the point where the force of the spring equals the weight of the mass of whatever is at the end of the spring, in this case a ball. So we were at 0 for this position graph. For velocity, at position 3, the spring has extended to its equilibrium length. That means it's at the maximum negative velocity. So the spring is given all the push it can give, and we've reached our V max, because once the spring starts extending past the equilibrium length, it's going to start pulling the other way. All right, so we have reached V max. And then for acceleration, at this point, the spring has fully pushed the ball, or pushed the mass. So our acceleration is actually going to be 0 at point 3. All right, so I'll go ahead and mark that with 0.0. And I'll tell you what, really quickly, let's go ahead and differentiate these colors so we can get a better separation of the graph. So we'll do green for velocity, since my arrows are up here in green, and we'll do acceleration in orange, since no real reason. It just looks nice. Okay, so let's continue on to point 4. Right, point number 4 is going to be right here, and here we see that the spring starts to extend past its equilibrium length. Right, we were at equilibrium here, now we're going to extend past it. That means that the spring is now pulling on the ball. All right, and so that's going to mean some interesting things for the acceleration and the velocity. First, let's take a look at position. Position, we're now below our equilibrium length, which means we're in the negative range, we're below 0. And so position is going to take a trip, or a dip, downward. Right, so I'll try my best to keep this all lined up. So position 4 is going to be negative, below the 0 point. All right, what about V max? Well, since the spring is slightly extended, it's going to be tugging on that mass, and that means the mass is going to be slowing down. So we were at our V max at equilibrium length. All right, now we're going to be slowing down and going back up towards 0. All right, so we'll draw another point there. And then lastly, we're going to get a acceleration. Now, the acceleration is actually going to change directions from a negative acceleration to a positive acceleration. So whereas before we were accelerating the ball downward, now as the spring extends past its equilibrium length, we're going to start accelerating the ball upward, which is going to cause it to slow down. Makes sense, right? So our acceleration crosses the 0 point and becomes a positive acceleration at point 4. All right. So now for point 5 onward, you might be able to fill in the blanks, but we're going to go ahead and do it the slow way anyway. So let's go ahead and mark out our point 5, and then 6, 7, 8, and 9. All right, these are all the points on the graph here, or on the diagram. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're at 4, 5, when the ball is at its lowest point, and the spring is most extended. So why don't you take a minute, see if you can get ahead of me here. What do you think is going to happen when the ball is at its lowest point and the spring is fully extended? All right, well, the easiest thing is going to be the position, right? That's probably the easiest thing to point out, since position is kind of already graphed. If you noticed, we've been following the position of the diagram. So at the lowest point, we're going to reach our negative position, right? So negative A, and that's going to happen at 0.5, right? So we got 0.5, lowest point. Now, what about the velocity? Well, we've been approaching 0 with our, from 0.4, from 0.3 to 4, we've been approaching 0. At 0.5, this is what's called the turning point, right? So at the turning point, we're actually going to get a velocity of 0. All right. So when the ball is fully extended like this, or the mass on the spring is fully extended like this, we're going to get a velocity of 0. Okay, so we started at 0, we went to a V max, and then we went back to 0. Now, what about acceleration? Well, the acceleration is actually going to reach its maximum point. All right, so we have our positive acceleration max, and we're going to reach the top of the graph here. And that also makes sense because the spring is fully extended. It's giving its maximum pull in the upward direction. That's the maximum positive acceleration it's going to give. So if we're going to diagram that on an XY coordinate plane, that is where we would put it, at the maximum positive acceleration. And likewise, where we started, that's when the spring was most compressed, so it will be the maximum negative acceleration. All right? Now, we spent a long time on this video. I want to be thorough, but I also want to wrap this up. So, this is going to be the inverse. From here on out, it's going to be the inverse of what we just did. So, the ball starts moving back up. We're going to get a little bit less positive acceleration. We're going to get a little bit more velocity as we move upward. And also our position is starting to bounce back towards the 0 point, towards the equilibrium line. So let's grab those 3 points. A little less acceleration at 0.6. A little more positive velocity above 0. Right, and then our position is moving back up towards the equilibrium position. Now at 0.7, right up here, we're going to get a lot of velocity. All right, we're at our equilibrium length, so we've gotten the maximum pull out of the spring. So we're going to reach our highest velocity, or our V max, right up here. As far as acceleration goes, we have no acceleration. We're at 0 acceleration because the spring is at its equilibrium length. So it's not adding any extra force. It's not accelerating the ball at all. So we hit a big 0 for acceleration. And then with position, we are back at 0 as well because of the because we're at the equilibrium length. So position is going to be 0 as well. And I know I keep on erasing points and redoing them. It's hard to keep track of where the horizontal line is without any sort of y-axis going on. So just trying to make it look as realistic as possible without any real guidelines for how to plot. All right, so position 8, it's going to be the inverse, but we're getting a little bit of compression from the spring. All right, so the spring is compressed a little bit, so it's going to be pushing down. All right, so we're going to have a little bit of negative acceleration. We're going to dip below 0 on our acceleration graph. A little less velocity. We're moving a little bit slower. And then our position is going to be slightly positive. All right, so let's graph that. A slightly positive position above 0. A little bit slowing down on our velocity. And a slight negative acceleration. All right, and then the last, we're going to end up where we started. So we started at A max, the maximum value for A, and we're going to end there as well because this is simple harmonic motion. It's going to repeat. So we're going to get back to where we started to, all right, and that's going to be a whole cycle, a whole period, a whole oscillation, right? Our velocity, our velocity is going to be 0. We don't move at these turning points where we start to change direction. All right, so velocity is 0, and we're going to graph that out. And lastly, our acceleration. Now this spring is fully compressed. It is going to be pushing down on this mass. It's going to be pushing down very forcefully. So we're going to reach a maximum negative acceleration on that graph. Okay, now here's the cool part. If we look at the points we graphed, we have something similar for each one. All right, we connect these points. We get what is called a sinusoidal function for each point. All right, so each of these represents a sine-like motion that is characteristic of simple harmonic motion. All right, you know, a sine wave is just a simple upward, downward motion like that. And that's what we have for all of these. They're sine-esque or sinusoidal. So we can use these in our formulas for describing simple harmonic motion. Because they're sine or cosine, we're going to use that a lot in our formulas. So both sine and cosine are sinusoidal in shape. They have this S-curve shape. They just start at different places. Sine starts at 0, so if we were to draw a graph and start at 0, that's where sine would be. And then cosine starts at a maximum position. So cosine starts up here, dips down, and then goes back up. Right, so that's a sine wave, and that's a cosine position. Notice how they have the same shape, just different starting positions. And you can't see that very well, so let me move the camera slightly. All right, there it is. Sine up here starting at 0, and cosine starting at some sort of maximum value. All right. Okay, so it's a lot to take in. Let's go ahead and give you the formulas, and then I will wrap this up. All right. So for simple harmonic motion, some things we want to keep in mind is our 3 formulas. All right. So for position, right, this is going to be x at a given time. All right, x at a given time. That is going to be the amplitude of the wave. All right, the amplitude, the highest point, times the cosine, because we started right here, right? So sine starts at 0, cosine starts up here. And then we're going to do 2 pi ft. Now, 2 pi f, that should look familiar. We should know that from the rotation unit, and that is frequency, all right? So 2 pi times f, that's going to be frequency, and that's also going to be in radians. All right, so we're going to be working in radians for this. So to make sure this cosine function works properly, you're going to want to turn your calculator into radians mode. All right, and then lastly, this t. So f is going to be frequency. All right, and then this t is going to be the time. All right, so if we're at 1 second, half a second, 3 seconds, whatever it is, you're going to put the time down there. All right, so let's go to the second one. We have our velocity function. Now our velocity function down here is a sine wave, so it's going to be pretty similar, except it's going to be using sine, and it's also going to use a negative. So vxt, or the velocity in the x-axis at a given time, let's make this a t, equals negative v max. All right, now let me pause right there. Why is it negative v max? So this is this is the amplitude, right? We're doing the same thing, but the sine function, it is a sine function, but it's actually upside down because it goes negative before going positive. So we have a negative here, and negative V max, that's the same value as A here. Well, it's not the same value, but it's the same idea of you're putting the maximum value in the equation. All right, V max, and then we do the same thing, 2 pi f t. All right, so there we have our velocity equation for velocity in the x direction at a given time. Now, for acceleration, what are we going to do? Acceleration looks similar. So once again, I need to move the camera a little bit. It's not ideal, but we're going to work with that just so we can see the bottom of the board. So we're going to do A in the x-axis at a given time. A in the x-axis at a given time. And I'm just making sure I got this down correctly. All right. So I'm going to do actually A acceleration times the time is going to equal negative A max, right, times the cosine. We're going to have another cosine function times, you guessed it, 2 pi ft. Right, 2 pi ft. Sorry we're a little sloppy there on the end, but it's the same as these. You have your maximum A, maximum acceleration, that's negative, times the cosine, times 2 pi ft. Oh, snap, I did not put the sine function in there. Right, sine. Okay, so gonna edit this part out, so we'll leave the formulas out of it and just explain the other part. Yeah.